So in this quick presentation, what I want to do is to kind of give you a guide in helping you to do one of the more important things that many people might tend to skip over in this section, which is really key to helping you understand and visualize what it is that the normal curve is telling us and how we can use it to help us avoid mistakes when we're doing calculations and give us a deeper understanding of how to input the values into our calculator correctly and to know when and where a particular answer that we're thinking is the correct answer doesn't make any logical sense. So I basically just want to go through some examples here and to help you, help to give you a guide into how you should be visualizing and working through these problems. All the ones that I'm going to go over here are using the Z-curve, but a lot of problems that you're going to be doing also involve just real data values. And really the only thing that changes for you when you're working with real data values is the numbers that are along your x-axis. When these are Z values, we always have 0 at the center. And the Z value basically tells us, how many standard deviations we are away from the center. But when we're dealing with real values, let's say that we had a population that had a mean that was equal to 100 and a standard deviation that was equal to 10. Then 100 would be at my center, and then we would have 110, 120, and 130 at my first, second, and third standard deviation. And then we would subtract 10 going in the other direction. So depending on what it is that the particular problem is talking about, you want to label out to two or three standard deviations in either direction. Okay, in this particular problem, I'm also in this section trying to help you connect some of the probability notation that's being given to you and what that means in terms of your picture and where to label things. Here, we start off with wanting to find the probability that Z, so a randomly selected Z-score, would have a value greater than negative 1.7 standard deviations. So looking at my well-labeled x-axis here, we could approximate the location of negative 1.7 as being somewhere between negative 1 and negative 2. So I'm going to just go ahead and label that out here, negative 1.7. And that's what you want to do also in your work is when we're talking about a data value, whether it's a data value or a Z value, marking out where that is along the x-axis. We want to know the probability that a z-score would be picked that's greater than negative 1.7. Well, all the values that are greater than 1.7 are going in this direction. And so I'm going to go ahead and shade this area that I'm looking at here. So with this stated here and shaded with the visual I have, I can know that my probability should be something greater than 50%. Now, why is that? Because at the center here, where 0 is, this is the point where we have 50% to the right, and we have 50% to the left. And so it makes complete sense that since I'm to the left of 0, and I'm shading to the right, I have more than 50% of my data shaded. Now, because I want to find this area here, and this is what I'm looking to do, normal CDF is the function on my calculator that I want to use to find that. And in normal CDF, we want to put what the lower boundary is, or you can think of it as the leftmost boundary, in first, and then we want to put the upper boundary or the rightmost boundary. And since this goes to the right and it's basically unbounded, we just have to pick an upper boundary that we know we'll never, that basically represents a infinity for us. So I'm just going to put 1,000, because if I were 1,000 standard deviations, I'd be well beyond several decimal points worth of accuracy here. Now, when we're using z, the mean and the standard deviation are always the same. The mean is always 0. That's the center of my curve. And the standard deviation is 1. So inputting these into my calculator, we get 0.9554. 0.9, sorry, not 9954, but 9554. And so that is the answer to my probability. There's a 95.54% chance that if I were to select a random value, that it would be more than negative 1.7 standard deviations to the left. So notice my connection here. This probability, I put what the probability is over there. What happened to my thing here? And then also what I want to do is to label my graph so that I know that this number here that I've found, that it is the value of my shaded area over here on my picture. Okay, we're going to do a problem, and the probability here is now the probability that a randomly selected z-score would be greater than 1.382 standard deviations to the right. So I'm going to draw in my normal curve. Somehow they didn't transfer over on my, when I transferred this over to this program, so I don't know what happened there. But regardless, let's go ahead and continue with this. So locating where the z-value would be along here, we see it's positive 1.382. Well, 1.382 would be somewhere between, there we go, somewhere between 1 and 2. So I'm going to put that here, 1.382, and I'm going to change the colors here so it's a little bit easier to see. And the direction we want to shade, we can look at this. This always, in fact, if you look at it as pointing, it's pointing to the right. And if your z is on the left, then we are reading this in the correct way. You always want to make sure z is on the left when you're looking at the direction it's pointing. When z is on the left, you can do that. And since it's pointing to the right, we know we're going to shade here. Okay, so what I can expect, again, is that my answer here, the probability, which is going to be the area that I find under the z-curve here, should be less than 50%. In fact, it should be sizably less. We know that 68% of my data is within 1 standard deviation, and we're outside of that with 68% in between -1 and +1. That leaves 32% outside, and so greater than 1 we know is 16. So this should be less than 16% here as far as my shaded area goes. So again, I'm using the empirical rule, if you remember back, the 68, 95, 95% rule to kind of give me an idea. But even if you just think of it as less than 50% and greater than 50%, that can by itself give you a lot of ways to avoid making mistakes. Now in this case, again, I'm shading to the right, so my lower boundary is static here, but my upper boundary is really unbounded, so I'm going to create a infinite boundary by putting in 1,000. But as long as you put in something that's larger than your standard deviation would tell you is a large distance, you should be okay there. We just want to make sure these are accurate to about 3 decimal places. So 1.382 is my lower boundary, upper boundary is 1,000, and this is my mean, and this is my standard deviation. which for z is always 0 and 1. If you had data that you were inputting as your lower boundary and upper boundary, you would want to put the mean of that data set and the standard deviation of that data set, if indeed you're not entering z values, but you're entering values that are data values. All right. Inputting this then into our calculator, you should get 0.0835, it looks like. 0.0835. In other words, 8.35% as my probability here, and also as my labeled area for my curve. And it makes sense. I don't even, before I click submit answer, so I don't have to go back, I want to make sure it makes sense to me, and of course in this case it does. Whoops. All right, for our next example here, we have something written in what I like to say, or what it's many times called trilinear inequality form, where z is in the middle. And the way we generally will read this, just so that if you were to read it straight from left to right, we would say negative 2.13 is less than z, which also is less than 1.681. But probably an easier way for you to read this, notice that z is written in the middle, is to read it as z is less than 1.681 and greater than negative 1.23. Now, why would I say greater? This symbol here is a less than sign. But notice that the z value is on the right of it. So really I'm reading it backwards because we want to read it in relation to z, because z is, the z that we're trying to describe is the area that is being described in relation to z. And so that's one way to read this. And the way, one of the reasons why I like this particular notation, because there's other ways you can do it, is because it does give us the ability to visually see z in the middle of two boundaries. On the left, I have negative 2.13, and on the right, I have 1.681. Oops, 681. And z, you can see, is kind of in the middle of those two numbers. So we kind of have an upper boundary over here and a lower boundary over here. And when z is in the middle like that with two less than symbols, that means what we want to shade is the area in between the two. Another way that this could be written is z being greater than negative 2.13, and, using the word and, z less than 1.6, sorry, terrible 6 there, 1.681. And is very significant, and we want to use that word because it says that and, if you recall, is really kind of the intersection of the two. In other words, we want the z's that are greater than this number and at the same time stop at this number. They're less than this number. And the only numbers that qualify this statement are the numbers in between the two. And so that's why this, even though this is a less than symbol, remember z is to its right, so it's still opening towards z, just like it's opening towards z here. In both cases, it's opening towards z, z being more or greater than the number 2.13. Okay, so in this case, I actually have my lower boundary, my leftmost boundary, and my upper boundary written here. Uppers should always be on the right, and lowers are the ones that we see on the left. And so we have our lower here, our upper here, and I can expect that this is definitely going to be somewhere greater than half, given my placement along the curve here. So negative 2.13 is here, and then 1.681 is here, comma 0, comma 1. And as we put this into our calculator, you should get the area here as being 0.9370. So that's my answer to my probability. The probability of selecting something at random is equal to this, which is also here displayed as the value of the shaded area under my curve. Remember that your shaded area can never be more than 1. And so not only does this meet that rule, but that's something you need to want to keep in mind as you go through these problems. Okay, another type of probability problem that we run into here is an OR statement. And if you recall, OR in probability meant addition, meaning we're going to add those two groups together. So I'm going to look at a description here. I'm going to shade these two descriptions, and my probability should be the sum of those two areas. So the first one says z is less than negative 1.456. When I get a 1.456 is somewhere between negative 1 and 2. So let's go ahead and put that in there. And then z 2.453 is somewhere between 2 and 3. And the first one says z less than, notice z's on the left and it's pointing to the left. So that tells me the direction I want to shade here. And this is z greater than 2.453. And so I'm going to want to shade to the right. Now, so there's two areas that I want to find that I want to also add together, because our OR always says that one or the other is acceptable. And in this case, what's acceptable is either this area or this area. Now, I could find these individually and then just add them up. But generally, basically, what I want is the sum of these two areas. So I could put this as a lower boundary, go up to 1,000, and find this area. Or I could start with my negative boundary here, negative 1,000, all the way up to this boundary, and then add those two together. But a quicker way to do that is to, with your normal CDF, type in 1 minus, then do normal CDF, and find the area in between these two and subtract that from 1. So in other words, use the complement rule. So negative 1.456 all the way up to 2.453, comma 0, comma 1. And if I take that result and subtract that from 1, basically what I'm finding on my computer is the area, or on my calculator is the area in between, and then we're subtracting that from 1, so we're leaving that out, and what we're left with is the total area within the two tails. So typing that into our calculators, you should get, as a result, 0.0798, which is both the answer to my probability and the total of my two areas. So this area plus this area equals 0.0798. Okay, now once you've, so some of the things I want to point out here, just in notation wise, when we were doing this, whatever the number here that we had, that ended up being a number that is always somewhere along the x-axis. And that's important to keep in mind. The number that is inside this parenthesis is being compared to a z-value. And since z-values are found along the x-axis, then this also here must be a value along the x-axis. And so as you're labeling this stuff, I highly recommend that you physically write this stuff along here. So like when I did this problem, I said, okay, well this is, about right here. And I went ahead and labeled it along, and I labeled it down here, so I'm not getting it confused with the area. And then when we shaded, to the right there, I also labeled that. And the answer to my probability is always an area. And so the area to the right always was labeled here. So I always recommend that as you draw these pictures, label your areas above, and then whatever's in the parentheses, that belongs along the x-axis. That way you don't begin to get these mixed up, because there are some problems where it's very easy to get those mixed up. Now move into the next section. We learn another function on our calculator, that is the invert norm function. And this essentially does the opposite of what the normal CDF does. Instead of putting a boundary, we enter our area to the left here, and it always has to be the area to the left of the value you're after. Then we enter the mean, and we enter the standard deviation of the data set, which of course for Z, if you're working with Z, is always 0 and 1. Okay, now you'll notice also, and let me just go ahead and draw these in here. Again, that's terrible. Okay, so you'll have to forgive me for that horrible normal curve here, but this does take us back to the empirical rule. And I want you to remember that. And so just a quick review that 68% of my data is within 1 standard deviation, 95% is within 2 standard deviations, which are our Z values that we're looking at here, and 99.7 approximately, and